small amount of atoms and speed them up and use the energy to get it rolling fast enough. And then once we can put that inside a body and we shoot in the body, if it was strong enough, it would pass right through. There'd be no interaction at all. But because we have this energy at 230 MeV, when we modulate that to that or a little bit less, we can control the very specific point in the body where that proton comes to rest. And as soon as it's down to its last tiny bit of acceleration, where it's almost stopped, that's where it transfers all its energy to whatever it's surrounding. So if we get it inside the tumor, the cancer tumor, when it comes to rest, just as it's coming to rest, it expends all its energy. It gives up all its energy to all the cells and that surround where that comes to rest. And that's how we destroy those atoms.
Does it produce these continuous rates?
It can. You probably, in fact, it will to a point. Not to the point that you feel burning so much, because every day your dose is just a little bit. But what we're trying to do is not so much create the heat. What we're trying to do is to create, transfer the energy so we damage or destroy the DNA and the cell, the cancer cell. So it can't reproduce, and then it just dies off in your body naturally and will just dissipate.
It's just the friction from the size of the proton.
It's really like it's like catching a baseball in a mitt, right? The ball's traveling through the air. If it was traveling in a vacuum, it would continue with the same speed, would never slow down. And as soon as you catch it and you stop it, that's where you're going to feel all the pain. And that's where you'll feel a catcher's mitt when you catch a baseball. There'll be a heat transfer. Not all the energy will go into heat, right? But you'll feel some heat because some of it's going to be given off in heat. And if you think about it, what's happening when we're treating a tumor is we have to be careful not to treat it too quickly. That's your dose rate. How much dose you receive and how fast you receive it. Because what's happening is it is burning. It is creating somewhat of scar tissue from a burn. So you're receiving a burn inside your body. If you receive too much, you're going to get too much scar tissue too quickly. Your body won't be able to compensate and really handle. Your immune system won't be able to handle dissipating and getting rid of those bad cells. But the other thing is you're going to start to feel it. And you start to feel this pain. Right? So it has to be done in a way that you're not killing the healthy tissue, you're damaging the cancer tissue, and you're doing it at a rate that your body can control and dissipate and get rid of all the bad cells once it's done. Right? Yeah.
Two questions. First of all, if it goes in, how much damage occurs before it gets to the prostate? And second of all, why don't you go more than 22 centimeters with more energy?
Okay, good questions. So the first one is, the reason that we use this physical proton is because we use what's called a Bragg peak. And what we've discovered and what we've known for a long time is when you use these light ions, which is hydrogen's very light atom, and you speed it up to that acceleration, that very little damage is done from the entrance to the exit. If you think about this, for instance, for prostate tissue, you'll be in treatment for 8 weeks, maybe a little bit longer, maybe a little bit less. And during that time, you'll be treated from both sides. We'll completely treat the entire prostate and damage all those cells. And at the very end, if all you receive is proton, you might receive, like your last week will build up enough that you start to feel a little bit like a sunburn. And that'll be it. That's the most damage you'll see. But you'll only see it on the entrance side because there is no exchange on the exit. If you get conventional radiation, X-ray radiation will pass through your body. It's causing the same amount of damage on the way in and the way out as it is for the tissue in the middle, which is why for conventional radiation, you have so many fields at so many angles, because what they're doing is the cross-section of every field, of every angle you receive, will be the cancer tumor. But what we do is you'll receive maybe 10 fields, and one field will be here, and you'll have the same volume in the center, but your entrance and your exit will be very specific. And if I change the angle a little bit, I still keep the cross-section of the tumor, but I use a different entrance area and a different exit. But eventually, even moving and keeping those angles, eventually I start to cause damage to the healthy tissue. So I have to stop. At some point, you have to stop. We'll talk a little bit about that when we get back out to the lobby. I'll answer some questions out there. Oh yeah, so here's the thing. This accelerator costs a lot of money. Weighs 200 metric tons. If I want to increase this, say, even if I want to go maybe 5 centimeters deeper, this is going to increase in price and size about 3-fold. Because the energy is going to have to increase exponentially. So there's another way to do that. We we could say, okay, let's not make this so much bigger for that. But what if we used a heavier ion? Because if we use a heavier ion, if we take a different atom, say we take carbon, and we say, let's do it with carbon instead of hydrogen. Carbon's a heavier atom. Well, to get that depth, I'm going to have to accelerate it to the same speed, but I'll get a higher energy because it's a heavier atom. But to accelerate it to a higher speed, this thing increases twofold. So either way, it gets expensive. And so we look at it and we say, okay, everything's a numbers game. So we get to a point we say, okay, if we can get to everything with a hydrogen atom at this size, and if we can't get to it from this angle, we get to it from this angle, but we should be able, if we just keep moving the gantry angles around, we can get to any depth we want, then our money says this is as big as we get. Now there are places in the world where we're using heavy ions or experimenting with heavy ions. I'm involved with a project in South Korea. Heavy ion project's been going on for about 9 years now. But the reality is the cost of building, running, and maintaining a system like that is very expensive, and it really, the patient population is a very, very small patient population that would benefit from it. So, but everything's more expensive. The power bill's more expensive, the equipment bill's more expensive, the shielding's much more expensive, and eventually you get to a point that you don't need to go any higher. Okay. And actually right now, the idea is there's people building smaller accelerators, not bigger ones, because financially say, okay, we can still treat 80% of the population we want to treat at maybe two-thirds the size of this, and then what they do is you need facilities like this to be able to treat that other one-third. Right? Okay, so we're going to head around the corner over here. Again, just